Okay, so basically we started with some fuselage frames and we looked at some basic designs and we started working on this one over here. Okay, so remember this is like, if you want, let's look at two flanges with 1, 2, 3, 1, 2, 3, 4 different stiffeners. And between each stiffener, basically there is a panel. Okay, it's not this is hollow, but this is a panel. So we went through how to find the shear flows on the panels, which we found by looking at this member DKH, member JK, CJK, and then AB. We were able to derive the expression for the Q1, Q2, Q3, and Q4. And we started working on the distribution in the stiffeners. So we started with the stiffener, we put in the two flanges, the top and the bottom, and now we're working on the stiffener. So we started looking at the stiffener DQH, which is this one over here. And basically, this one is just like in solid mechanics that you need to basically do the beam. And in order to see what will be the shear bending moment diagram, you need to make cuts every time there is a discontinuity in the loading. So the first cut will be between D and K, and second cut will be between K and H. So we look at this, we only, the assumption we're making is what is the assumption that Janet you make in any structure in aerospace or even in solid mechanics when you study trusses? What was the assumption about the truss members? Equilibrium. Okay, equilibrium, so you can use summation of force equal to 0, but what else? What about these members here? BK, CG, and these ones over here.
Vertical members carry vertical load.
They carry vertical load, correct? I mean, that's why we say vertical members will support the vertical loads, horizontal loads. But that should lead to the answer that these members is something you call in solid mechanics one force members. So they only will carry load in the cross-section direction, correct? You assume not to carry any bending. All right, so they only carry loads on their direction, on the actual direction. Okay, so that's why in that figure over here, I'm only doing the shear force, so the normal force here, FDK at the cut, and I'm not doing any bending. Okay, that's because that's the assumption of one force members. Okay, so that's what we did over here. So we get the FDK equal here to 2,257.1. And we did the first cut over here. Now we need to do the second one, which will be between K and H. So we follow exactly the same procedure. So I just make this one a bit longer. Let's say 3 over here. We make the cut. So this is still our point D. Left-hand side, we have here. Now we're gonna have here Q1. And we're gonna have some Q2 over here. But this will be here point K. All right, we know that distance here is 200. I'm looking here at the figure, okay? Taking everything from that figure, 200. And we're gonna start here the S. From here as well. But now what else do we need to add? We need to add here the force. F1. Equal to 4,000 newtons. And here the angle 60. And we're going to look now at the actual force FKH. So as before, in order to find this, you just say before, you assume that everything is in static equilibrium, so you can use summation of force is equal to 0. It should give us what? So if we look at the Q1, this will give us minus 200 Q1. So this is Q is shear force. Remember, it's force per length. So it will be Q1 times what distance? 200, no? Okay. Now we're going to have here minus Q2, this one over here. Much is our moving? We'll be moving all this From here, water is going down, all that distance here, minus this one, no? So it will be S minus 200. Does that make sense? Okay. Now, since the assumption is these are one force member, so we only need to look at one component of the force 4,000, just at the vertical component. So what would that be? Plus 4,000 cosine 60 plus F KH equal to 0. So remember, Q1 and Q2 are known. Let's see, what was Q1 and Q2? When we solved, we had Q1 to be approximately equal to 11.3, and Q2 to be approximately equal to negative 2.5. So to 2.57, because you were looking at the magnitudes, okay? So 2.57, not the minus sign.
Oh, sorry, so I have a question now, why is there 200 twice? So it's minus 200 Q1.
It's true, but you're right, it should only be once. I don't want to put it twice. Correct. Thinking about force times distance. I don't know why I put 200 initially. But thank you. Okay, here we go. So we are good over here. So we do this calculation here. This is going to give us that F AH will be equal to negative 2.5709 S plus 771.28. Okay, so if we do the calculation, this will give us at 200. So at this point right here, so it's 0 over here, at 200, that will be equal to 257.1. And FAH at 300, if you do the calculation, is approximately 0. Okay, so if I do the plot of the actual force on that member, so let's see, let me just do a little quick sketch of the member here. So we see how everything will look like. D K H, and we know here we have Q1, Q2, here 4,000 at 60. When we look at the figure here, we have what? SDK at 0, if you want to add it, is 0. And then at 200 is 2,257.1. So we go from here, 2,257.1. We are from the first cut. The second cut, we see there's a jump. Here is 2,257, we go to 257.1. So it would be a jump here to 257.1. And then at the end here we have 0. Okay, so we're gonna do one more member and then I will give you the result for the other ones. So let's look at the stiffener. So let's see, that's the stiffener that goes, okay, so over here. The one that has also the load at the end of 5,000. All right, so here we go. I'll do the figure over here. On this side is Q4. This side is Q3. That side is 5,000. And we know the total height of this member is 300. So in this one, we are lucky. How many cuts do we need to do in this one? Just one cut, no? Okay. So let's see, this will be B and F. So if I do one cut over here, we have B. Here we have Q3. So we have Q4. And this side here will be S. Okay, and here we'll be calculating now the force. FPF. Once again, we do summation of forces equal to 0, which will give what? Q3 times S minus Q4 times S plus FBF equal to 0. So from before, let's see what we had. We had that Q3 approximately equal to 6.67. Q4 23.33. So this gives F of BF equal to 16.667 if you want S. Okay, so let's see if you understand this. If we did this correctly, what should be 300 times 16.667? What should be the value of the actual force at the tip? Should be 5,000, no? So probably you do 16.667 times 300. I'm pretty sure you get, 3 times 1.667 is 5, no? Okay, so we'll give you the 5,000. So again, if we need to do the diagram again, B, F, 5,000, Q4, Q3. So what you will find is that it goes from 0 to 5,000 over here. Okay, you don't have to do this, but if you want, you can do it. Same thing over here. If you want, you can do this to show it, but you don't have to. Any question about the procedure? I mean, basically, it's all the time the same thing. Now you take the member, you see how many discontinuities you're gonna have, you make the cuts, and so on. So over here, I'm not gonna do the detailed calculations. I'm just gonna say over here, following. A similar procedure you would get, for example, that stiffener CG will have the following distribution. So it will be C. So this is a C. Here there is a J. Here is a G. Actually, what you find on this one is that you get to minus 923.1. Here you go back to 0. But this number, since this is negative, it will be in compression. Okay, so I'll skip the details, but basically if we go now at the stiffener JK, which is the horizontal one. So that's you're gonna get, let's see, I'm just gonna give you the figure. You will go here from 0 3,464.1. Okay, so following a similar procedure, let me pause here for a second. So I know this is something that is not required for the class, but I highly encourage, is that if you look the other day on this class where I went to, let's see, models, I put here an Astra model. Okay, so if you do it, okay, it would be a good practice. Generally, I do it in class when you have computers in class, but since we don't have, we cannot do it. Let's see if I have it saved somewhere. No, AE418 should be at the top. So let's see if I have Nastran saves. Hopefully it's this one. So basically this one, I mean, you will come up with this one, this model, let's see. Flange ABCD. I think what we had was what for the flange ABCD? If you look at your notes, we did this stuff. This is EFGH. So it's this one here, you see. All right. Basically, you see, it goes here from, oops. If you look at the camera, that's what we have, no? With this value here, 4,488, 2,080. Obviously, it's not going to be perfect because of the mesh size. But if we put now the, let's see, F5 criteria, it should be within that range over here. I mean, let's see. What was FA? So it was 10,000. If we look at this one, was 10,000 to 323, okay? You look at the final element, is giving you 9,943.1. The reason is because it's taking the average between the tip and the next element, which is over here. Okay, so if you look at this one, it's giving you the average between this point and the next element on the mesh, that will be right here, no? But you see, basically follow the same behavior. Let's say we take this one, doesn't look like I have it, but maybe we can keep it. Show full model. Let's take maybe, let's see the element at the tip. How can we do this one? New group. What was the one at the tip? DKH, I think, no? DKH. It's not that one. Pick it up. Okay, model per group. Let's see, elements, ID. Okay, here we have the value. What was the shape we had? So let's see, F5. I think beam diagram. Remember what was the shape we had for this one? Is that one we just did? For this one, we had this one over here, no? So you see it is here to 2,257 to 257.1 and then 0. Here it can sort of follow kind of the same behavior, no? Okay, again, if you do F5 and look at the criteria, basically, we don't get exactly the same values, but this should be 0, 138. Here you see the jump, no? And so on. But basically, show the behavior and results will get better. I know you have done some basic finite elements. The result will get better if you do what? If you do the mesh smaller, no? You take more elements. Okay. So again, it's not mandatory for this class, but I highly encourage you to do this at home. If you want to learn something and even check your homeworks, no? Or assignments. Okay. So you can do this. There is a video. And I will put the videos, but it will not be required for the class. That's why it's not part of the grade. Okay. Okay. So let me arrange the notes. 6, 5. Okay, any questions so far? All right, so done with this section. This is not difficult, can be tedious as work, but this is not difficult. Okay, so end of this section. Oops. There we go. End of this section. Okay, so that's something you have done in structures 1, but shear flow approximation in a box slash frame. So if you have any type of structure that can be made of this, let's say, so you have here, let's say you made up a spar or a wing with 2 spars, 2 ribs, okay? It's just one section. And you know you have a shear force V going this way, where V will be the shear force, and your height of your structure is H. So what is, and I'm going to tell you, this is what is done in real life. What is the basic assumption to calculate the shear flow? Q. What is shear flow? It's force per unit length, no? So let's say you need to find the average shear flow in this cross section that might have a panel. Going to draw this panel. What do you think will be the simplest assumption? Force divided by height. Does that make sense? Okay. And if you look at this, what should be the 2 numbers that really will be resisting this load? This one and this one, no? In our approximation, we assume this one and this one will not resist anything. However, the load here, the shear flow that will be transmitted over here, it will then be transferred within the panel this way, no? Yeah, does that make sense? Okay. So now we're going to do something a bit more complicated, is how to determine the shear flow that goes through a curvilinear member. Okay, so imagine that now you have a member here. Let's say you have this, you can have the same thing over here. Let's say that now you have here the front of the wing. How do you determine the shear flow going through the curvilinear member? All right. That's something that maybe you have done in structures 1, I'm not sure. Page 9. So how to find, how to find shear flow in curvilinear member. Okay, so here I'm going to do a basic figure. Again, maybe you have done this in structure 1 or not, I'm not sure. Let's say this is 1, this is 2. Let's say this is point O, like the center, like if you need to the curvature, you can take it from this point. Here I'm doing counterclockwise positive. This will be Q1, 2. We'll start calculating from here. Let's say it will be S. E and perpendicular, all of these are values that I'm putting. Okay, and one more thing. So this time, this is going to be subjected to, you see, counterclockwise, so positive moment, and 1, 2. So here, the trick of this one, let's say you take here an element, like a piece of cheese. This will be dA. So you kind of agree that if dA is small enough, it should be like the area of a rectangle, no? Sorry, of a triangle. How do you find the area of a triangle? You do base times height and you divide by 2. Okay? So in this case, what will be the length of this one? Will be T, which is all this length over here, T. The amount is moving on this side. Let's say we take an element called BS. So height times width, and we divide that by 2. In this equation, you can determine that P S will be equal to 2 times the differential area. Or you can approximate, say that PDS over here will be equal to 2 times the area of that element. So knowing this, we can now the moments about point O and equate this to 0. Positive counterclockwise. So this will give what? M12, which is the moment over here. Now, the shear flow Q12 recreates a clockwise moment, so will be negative. So remember, this is force times what? Length, no? In this case, what will be the length? S. Okay, S, or we can say, let's say, instead of S, it's S, but let me just rewrite S as maybe ds between 1 and 2. Okay? If you don't know that distance, times what? P. Times P. Equal to 0. So basically here you're gonna have that M12 is equal to Q12 times the integral of PDS, which you can do using this expression. If you know this length, you can do it, okay? It's not an issue. Sometimes that's the way it's done. But otherwise, what could you say? M12 should be equal to what? Q times 2. Q12 times A, which will mean that M12 will be equal to 2A Q12. Okay, so I don't know. Have you seen that before? Does it look familiar? Yes, no? Okay, the 2A. Okay, so that's, I'm sure you have done that to find the shear flow in open section because you need to do it as well. Okay, perfect. I know you know this, but what is the difference between, so this is the end of this one, statically determine the problem. So that's the problem that can be solved using summation of forces and summation of moments only. So basically, if you had a 2D problem, what does that mean? What is the maximum number of nodes you can have? You can have 2 equations for the x, summation of forces on the x, summation of forces on the y, and the moments about the z, no? Yeah? Okay, if it was 3D, what is the maximum number you can have? On the extreme will be 6, but generally it's not going to happen, okay? We rarely see 3D problems in this. But basically, statically determined means that you can solve with the static equations. What are the static equations? Summation of forces equal to 0, summation of moments equal to 0. Okay? So now, if you have a problem which is statically indeterminate,
And
Yes,
I was wondering why you can't have 4 unknowns for it to be a problem. Because
yes, you can have, because generally is in 2D, generally if you have the rotations, it will be, for example, you have here the board. Let's say it will be the X, it will be the Y. This can only rotate about the Z from inside or outside the board.
what would be the unknowns? Like FX and FY?
It will be Fx, Fy, and Mz. Okay. So statically indeterminate, what does it mean? So basically, this cannot be solved with summation of forces equal to 0, summation of moments only, requires additional equations. And this is generally the main topic of this class, structures 2, is to solve statically indeterminate problems. So that you need additional equations in order to solve them, not only summation of forces or summation of moments. Okay, so the next example is the last example we're going to do in class that is statically determinate. Actually, the problem is statically indeterminate, but we're going to solve it making the assumption to make the problem statically determinate. And we're going to see why this is a valid assumption in most cases. Okay, so if you want, I give you now the idea. If you have a member, if you look at the truss, okay, you know a truss maybe can have like a rectangle, and to be statically determinate, you can just put one bar, no? For stability. Okay, you can solve this one with statically determinate. What happens if you decide to put another bar on the other direction? Now, the problem is statically indeterminate. But is it safer than the first one? It has 2 members instead of 1 inside, no? Across. So let's say you do your analysis for the structure with only 1 member going on that direction. Okay, going across. And you find out that your structure is safe. Can you make the assumption that then the structure will be safe if you put 2 bars in the middle? Yes, no? Okay, so that's what I'm saying. Sometimes you can have a problem which is statically indeterminate, but you can solve it saying that it's statically determinate, making the assumption if it is safe, solving it as being statically determinate is going to be safe with the extra members because it will be statically indeterminate. Yep.
I think your screen sharing is still paused.
Oops. Okay. How long? So we will go here or
The green triangle.
this one. Okay, so basically, I think maybe this is not recorded. I think I stop it. So we look at how to find the shear flow in the curvilinear. We say this is the element. We look at this element here will be length, which would be P times width ds divided by 2 for the area of a triangle. This is what we have. So we can approximate the term PDS by 2a. We take the moments about 0.0. So moments, shear flow times distance, which will be ds between 1 and 2, times the arm P. And we get this expression over here. You can calculate M12 using this expression, or you can approximate it with this expression here. We're saying that a member statically determinate is one that is a problem that can only be solved using the static equations, and that a problem statically indeterminate is a problem that needs the static equation plus some additional equations. Okay. And then the next example we're going to do is actually a problem that is statically indeterminate, but we're going to solve it making the assumption that is statically determinate. And that assumption, in most cases, is valid because if the structure is safe as being statically determinate, it will only be safe being statically indeterminate. Okay, it depends how accurate you want to be in your result, no? Okay. Okay, so let's do that. So example. Again, this will be the last problem that we do that is statically determinated. After that, no more. So let's say we have here windbox like structure. So this structure is, this one could be solved statically determinated, but let's say we add here one member in the middle, and that we have here a circular member. So we have here 1, 2, 3, 4, 5, and 6. Okay, we have a shear force on the x direction over here, and a vertical shear force Vy acting at 3. So we know Vx will be equal to 12,000 newtons. Vy equal to 8,000 newtons. That distance here is 600. This one here will be 200. This one will be 200. So at the radius over here, this is also so again, this is you have panels, okay, on each one of these members. So here you have Q1. So I think we already mentioned why they follow this direction, because you need to be able to use summation of force equal to 0. So it needs to be 0 on the x and y direction. So it'll be Q1. Here you will have Q2. It will be here Q3. Okay, and the question in this one is to determine Q1, Q2, Q3. So what we're going to do here, we're going to do the assumption. Assume the above structure is statically determined. Okay, so let's say here 3 unknowns. All right. So in order to do that, so statically determined problem. So this becomes this. That means we're gonna have now. So I'm simplifying the problem to this. That means we can only have 3 unknowns. So the 1, 2, and obviously you can do different assumptions, but this is the assumption we are using for this problem. So we're gonna have here Q12, Q41, and maybe I should have not done the 3 over here, but here a long one, Q24. Okay, and we still know here there's a force dx. Here a force dy.
That would be Q.
No, because you skip 3, you go Q23, it will be the same. You want Q23, we go to Q34. Yes,
Why can't we skip 2, just do Q14?
you could do that.
But
But you can, that would be your assumption, but this is the assumption we are doing.
the answer you did.
Correct, your answer will be different, yes. Okay, so you want here Q12, Q24, Q41, shear flows in flanges, or flanges in this case, I think is the best word, and not stiffeners, because they're the main members of the structure. So if we look at this full structure here, now we do summation of forces. Let's say on the X. Okay, so we make the assumption right here, that what will be the members carrying the Vx force? So let's say we have here Vx. What will be the flanges carrying this force? Should be this one and this one, no? Yeah, the horizontal. So we know that distance here is 600. 600. So we have Vx is going to the right, minus 600 Q12 plus 600, you want to be here, should be Q, I mean, we can say Q34 if you want here, but you know that Q34 is the same as Q24, no, in our assumption. Okay? And this should be equal to 0. So Vx in our problem is 12,000. So if you substitute the values, you're going to get one equation that will be equal to Q12 minus Q24 equals to 20. And this will be our first Q12, yes. Next, we can do something similar. Summation of forces on the Y. Where are you going to have the Y? Plus 400 for 1. And now, let's do an approximation for this one here, for the Q24. What could be an approximation for that one, based on what we said before? What is that page? What do we say could be an approximation for the shear flow What structure to do the shear force divided by the height, no? Okay, so we could do an approximation. Again, this is approximation assumption, so it's more than one way to solve this problem. So now we look at Q24, we could do what? Minus, so this is, if you remember, this is 200. Will be minus 400. Q24 equal to 0, and Vy was equal to what? 8,000. So from here, we can have the approximation of Q24. Yes, minus 241 equal to 20. Two equations, you're gonna have three unknowns. So what does that mean? We need to find a third equation. What's gonna be the third equation? Correct, about the z-axis, no? Okay. You want to put here x and y. Would be page what? 10. This problem is really just as an example, okay? Because this is the most difficult ones, to tell the truth, because in order to find the solution, you are making assumptions. So depending on your assumption, your solution will be different, no? Okay, so it's a simplification of the problem, but everybody can simplify this differently. So now we do summation of moments. So with summation of moments, what are the two things we need to specify? To specify what do we use as positive direction. If you don't put anything, I will always assume to be counterclockwise to be positive. And here we're going to take the moments about 0.4. So before I do this, let me just redo a figure since we don't have it in front of us. That's not good at all, but you can do better job than me. AQ 1, 2. Q 2, 4. We know this is 200. So this is R equal to 100. This would be 400. And that distance here is 600. Okay, so we take moments about 0.4. Let's start with the Q12. So what is the value of the force? Value of the force will be 600. Q12. What will be the R? 400. Will that moment be clockwise or counterclockwise? Will be counterclockwise, so that's positive. Say it again.
Can you, there's a.
Oh, sorry. All right, so we have this. I forgot to put something on that figure, is that we also have here the VY. Here we have the VX. The first one. Now let's look at the shear flow Q24. So that one should be equal to what? With the approximation we did before. I mean, there's two ways to do it, but if we use, it's not the approximation, if we do the calculation we did before, what did we say? This would be equal to 2AQ12, no? Yeah. So again, you don't have to do it this way. Later on, we do it in the two different ways, but here let's do it that way. So in this case, what will be A? It's about 0.4. So you look at 2Q24, so A should be area over here. So I mean, we get here plus 2, and this will give a counterclockwise moment, so positive. So this is 2. What will be A? Let's first look maybe at this member. This member would be what? This triangle would be here on this triangle. 600 times 400 divided by 2. So what will be the area of the half circle over here? R squared, which is 200 squared divided by 2. This stuff would be times Q 24. So again, all this member over here, this is A. What would be the moment created by the VX force? Would be clockwise or counterclockwise? Would be clockwise, so that would be negative. What would be the value of the arm? And what would be the moment created by the VY? Clockwise or counterclockwise? So negative, clockwise negative, and the arm will be 600 equal to 0. You do the calculation for this. This is going to simplify to Q12 plus 1.5236 Q24 equal to 30. And this should be your equation 3. So that means what? That we have our 3 unknowns. Q12, Q24, and Q41. We have 3 equations. So what can we do? We can go and solve. Okay, so the way we do this is first solving first 1 and 3, which would be the equation Q12 minus Q24 equal 20. Q12 plus 1.5236 Q24 equal to 30. You see the same variables. So when solving this one, you find Q24 equal to 3.96 newtons per millimeter, and Q12 equal to 23.96 newton per millimeter. Finally, you substitute into 3. What you're gonna get is, what is it, Q24 and it's Q41 equal to 20. So from here you get Q41 equal to minus 16.04 newtons per millimeter. Yes,
Why can't we take around 0.1 as our moment?
you could take about 0.1. It doesn't matter about which point you take it.
I got a very different answer.
More zero and what?
Q12 or the Q24.
I mean, it doesn't matter. It should not matter about which point you take the moments.
Right.
Okay, conceptually, it doesn't matter at all. Okay, so now we're almost done. So this is the flows in the flanges. So 12 shear flows in panels. Sometimes they call it webs or skin. So again, let's redo a figure. Okay, so remember, we're trying to solve, we're finding an approximate solution for our statically indeterminate problem, assuming statically determinate. So we have 1, 2, 3, 4, 5, 6. Here we have Q1. Here we have Q2. Here we have Q3. Okay, so if we look at the member, or yeah, let's say flange 154. Now this is similar to what we did before. So basically we go now to the solution we had before. 1, 5, 4. What should we have here? We should have here Q2. Here we should have Q3. What is all the shear going in that direction here? This is what we call Q41. That we just say would be equal to what? Yeah, we need to be careful here. Okay, if we put it this way, we had it plotted going up, no? Before. Yeah, and we find out that it's equal to minus 16.04. So actually that means that it's actually going down, no? Okay, so personally, I think it's better to do this figure the other way. I think I like it more than this way. I will do 1, 5, 4. I will put here Q2. I will put here Q3, but here I will plot this one this way. I will just put the magnitude to be 16.04, no? Okay, so for me, I think it's easier. And remember, this is 200. And this is 200, the distances. So once again, if we do the summation of forces on the vertical direction, what are we going to get? We're going to get 200 Q2 plus 200 Q3 minus 400 times Q41 equal to 0, which this is going to give us the equation Q2 plus Q3 equal to 32.08. Let's call that equation lowercase a. Now, if you want, I'm going to look at I'm not going to call it plan, I'm just going to call it stiffener, because it's really stiffener, 5-6. So let's see what we have in 5-6. So 5 is to the right, 6 is to the left. So you look at this, on top, you're going to have the Q2 going to the left. I think you realize you need to see at this figure, okay? The Q2 going to the left, and at the bottom, you're going to have the Q3 going to the right. And what do we have at 0.5 acting? Here we have here the Vx, here the Vy. So I put here Vx, which is equal to 12,000. So we do the summation of forces equal to 0. This is going to give us, so what is that distance? It's 600. So it will be, let's see, 600 Q3 minus 600 Q2 plus 12,000 equal to 0, which will give me the equation Q2 minus Q3 equal to 20. So now what can we do? We could actually solve these two equations for Q2 and Q3. So solving A, B for Q2 and Q3, we get that Q2 will be equal to 26.04, and that Q3 will be equal to 6.04 newtons per millimeter and newtons per millimeter. One more, we need to find Q1. So I do Q1, we need to look at which member? We need to look at the member 263, no? Okay? And we'll be done. So stiffener 263. We have 263. We have Vy here equal to 8,000. We have here Q2, Q3, and Q1. So this is 200 and 200. So we do the summation of forces. We're gonna get, so let's see, 400 Q1 minus 200 Q2 minus 200 Q3 8,000 equal to 0. So we do the calculation. This is going to give you Q1 equal to negative 3.96 newtons per millimeter. So once again, this problem, the numerical value is not that important. Important part is the little sketch I'm going to do next. So in your conclusion, let's say we have our problem. That was this problem over here. And 1, 2, 3, 4, 5, 6. Panel 0, panel 1, panel 2, panel 3. That is statically indeterminate. Simplify it. To this problem here, statically determinate. If you want to do this, this, and this, that's all we had, those three members. Okay. This would be simplification or assumption. So we have 2 minutes to write it down. So why this approach is valid? What is our conclusion? What we said at the beginning is we can say that if structural is found to be safe statically determinate. So let's say less members or flanges or stiffeners, okay, less members, comma, it is valid to assume the structure be safe for the statically indeterminate system. Okay, so again, here the purpose of all this is not the example, is to show you that sometimes if you get a first approach, so when you do the design of a structural component of the wing, okay, you don't start right away with the most complicated plan, no, when you do the design. You start with simple assumptions, correct? When you do your basic design. Simple assumptions, you want to simplify your plans as much as you can. So you first make it statically determined. You say it's safe. Now you say, okay, I want to make it more detailed. Let's say you want to remove weight. So now you want to remove weight, what's going to happen? You're going to have to make the analysis more precise, meaning you need to go statically indeterminate in order to be able to remove material. No? Because in this case, how many members you have? 1, 2, 3, 4, 5, 6. No, you have 6 members. In this one, how many you have? 1, 2, and 3. No, okay. So yes, this one can be saved, but maybe you are paying a weight penalty. So let's say you do your initial design with this, and your employer is happy with the weight, with everything. Why are you going to do this statically indeterminate? Let's say your employer says you need to remove whatever 10% of weight. Then in that case, what do you need to do? Now you need to go back into that system and make sure that if you change the diameter of those flanges or stiffeners, it's going to be safe as well, no? So now you need to get into more detailed analysis, which would be the statically indeterminate, which is what we'll be doing starting next class. Okay, that's all.